Hello, everyone. Welcome to the 2024 Dresselhaus Lecture. It is an honor on behalf of MIT.nano for me to have a chance to stand in front of you. And on behalf of MIT, welcome today's Dresselhaus Lecture, who I'll introduce in just a moment. My name is Vladimir Bulovic. I'm the director of MIT.nano, and I have had the privilege of knowing Millie Dresselhaus for many years, and had the privilege of being inspired by her example many more years that followed from the moment I met her. I'm absolutely in awe that I have a chance now to introduce her namesake lecture in order to carry the mission and the vision of what Millie has indeed given to many of us. Commitment to both fantastic science and commitment to humans around us, building upon the opportunity of building that science and human community that will define tomorrow. Thank you for being here, and allow me to introduce the Dresselhaus Lecturer in this 2024 edition of the lecture. We are very lucky to be hosting today Professor Clare Grey, or as I was told by a colleague, the appropriate title would be Dame Professor Clare Grey, Ordinary Dame, Commander of the Civil Division of the Most Excellent Order of the British Empire. It is truly an honor to have you here in many reasons. But most importantly, we are looking for inspiration that indeed we know you carry. Professor Grey is a Royal Society research professor and the Geoffrey Moorhouse-Gibson Professor of Chemistry at Cambridge University in UK. After receiving a BA and doctorate from Oxford University, she was a postdoctoral researcher, after which she joined the faculty at Stony Brook University in 1994, becoming a full professor in 2001, and then moving to Cambridge University in 2009. She was a director of Northeastern Chemical Energy Storage Center, a US Department of Energy Frontiers Research Center, and then associate director. She's currently director of the EPSRC Center for Advanced Materials for Integrated Energy Systems. She's co-founder of Niobolt, a battery fast charging company. Her current research interests include the use of solid-state NMR and diffraction-based methods to determine structure-function relationship in materials for energy storage, conversion, and carbon capture. She received many, many honors. Most recently, these include Hughes Medal, the Kerber European Science Prize, and the ACS Central Science Disruptors and Innovators Prize. It is an incredible honor to have you here with us, and I would ask you to take the stage and tell us about your own work. Please. Thank you.
So it's truly wonderful to be here to celebrate the life and the science of Millie Dresselhaus. And I knew Millie not very well, but I worked with her particularly through a workshop in Rüsselsheim for a number of years. And this is Millie with a very diverse group of scientists, two women, Millie in red and me. This was Millie when we were doing outreach activities to some of the scientists who'd come from various Arab Emirates countries. And this is Millie when we went up to the top of the mountains to watch the sunset with Sheikh Saud, and she's there very much engaged in a conversation with him. He then responds equally vividly. So she was a wonderful person in terms of interactions, and I'm sure people in this audience obviously know this more than me, but there were perhaps PhD students who haven't had so much of an opportunity to interact with her. And of course, it wasn't just about that, it was the wonderful legacy of science. And what I'm trying to do today is I'm going to talk about some different things that I don't always talk about, particularly inspired by some of the work of Millie's, and just to sort of look at the papers that have been instrumental to some of the thinking of what we've been doing recently. It's this wonderful review in 1980s where she pulled together a whole mass of different structural electronic properties of graphites, starting with some of her own work in 1965, and this was one of the second papers in 66 on spin-orbit interactions, very classic work on intercalation compounds, and of course she was a very strong advocate for women in science, and this is an article she wrote, as early as 1975, and if you've spent a bit of time reading it, she's there stressing, this is in the conclusions, that diversity is important because it brings all of the larger community into doing science. So I'm honored to be here to give a lecture on her behalf, or in honor of her rather. So with that as a link, I just wanted to start by saying I'm going to talk about batteries. And of course the battery, the lithium-ion rechargeable battery was put together in Sony in 1990. It was to power their camcorder. So I'm sure that many of the PhD students in the audience have probably no idea what this thing even is. But it was, it was Sony that wanted it, they weren't a battery company, they were desperate to have more energy density. And of course it was the combination of people like John Goodenough and others with the lithium cobalt oxide chemistry, but then on the carbon side it was people working in carbon, of which Millie was very much one of them. I like to put this paper up from John Goodenough, where this is the first paper on lithium cobalt oxide in mat-res ball, just to remind also the PhD students in the audience that you can get a Nobel Prize with a mat-res ball paper. It doesn't have to be in Nature and Science. So reflect on that when you're... So I'm here, and I don't again have to tell this audience that batteries have really transformed the way we live. The ability to be able to access information on the fly. They really have underpinned the portable electronics revolution, but why we're working on them now is associated with climate change. So these are pictures of the icebergs in Iceland that are melting faster. This is in Cambridge, and when I say Cambridge in this conversation, I mean the Cambridge. And this is flooding in Grantchester outside Cambridge from excess rain the other day. And so it's the sort of possibility of using batteries to try and reduce carbon emissions and also pollutions. So if you just think about transportation, batteries are good enough. We have cars that are around, and they're cars made by people, I don't want to be political here, but who have become very important in the last few months, but they're still too expensive. And I think Jet and I were talking about some of these things earlier on, and we'll continue a conversation afterwards about some of these things. But the question we have is, how do we produce batteries at the cost that are suitable for mass adoption globally? So it's not just if you live in Cambridge, UK, or Cambridge, US, and you can afford to buy your Tesla. It's how do you do this to electrify the planet? And the biggest challenge is really, how do you make batteries to allow more renewables on the grid? So you need batteries for dealing with short-term fluctuations, but you also need the ones that are much more of a bigger challenge for the long periods of time. So at the moment the sun is shining, so you're okay in the UK, in the US. In the UK this time of year we have no wind and we also have no sun. And that's one of the biggest challenges. And I think just to get the context of scale, the UK has 2 pumped storage locations, and one of them is a mountain inside Wales where the whole of the mountain's been dug out and you pump the water up and down, and that has a storage capacity of 9.1 gigawatt hours. This is the Tesla mega battery. Now there are bigger ones than that, but you can see that the challenges of scale. And so how do we do this in a sustainable way? And then we think about the chemistry that's out there. Since the lithium cobalt oxide battery, graphite battery I was telling you about, the energy density has gone up by about a factor of 3 or 4. The price has gone down by more than a factor of 10. But if we're going to really make step changes, we need to come up with new chemistries and come up with new materials that are both more sustainable and more safe, and think about other issues like second-hand use, which then mean that we have to make batteries that last longer and that we have to do them in a safe way. So this is a little picture of a Samsung Galaxy notebook. Those of you who fly may recognize the back end of an aeroplane seat. This was the one that caught fire on a plane. And this was an incident because Samsung tried to put the same amount of battery in just 5% less space. And so as the battery expanded and contracted, parts moved and it ended up short-circuiting. So to think about sustainability, if we just imagine and look up the numbers for all of the gigafactories that are being built globally, they need more tons of cobalt than are actually being mined from the DRC in Congo with all of its mining issues. Even lithium mining has sustainability issues. These are the salars in this particular one is in Chile, and you can see the flamingos feeding on the algae there. But as the companies are coming in, they're pumping out the brines, they're left to evaporate. So the water's draining there, there's evaporation issues elsewhere, and it's affecting the whole ecosystem. So this is the global challenge that we have to think about to try and increase the diversity of different minerals that we're using. So in order to improve batteries, and this is, I'm just preaching to the converted here, we need to understand how they work, we need to understand how they operate, and we need to understand how they degrade. And the challenge is that some of these processes happen in picoseconds to milliseconds, but yet they're going to manifest themselves in the days to hours to years that you might use your battery for. And so how do you think about and how do you tease apart the relevant processes? And it's not only the time scale issue, it's also the size scale issues. You have to worry about particles small and what the atoms and electrons get up to, but you also need to worry about what the particles do and what the pack scale do. But we're here in a university, and so it's our challenge to really understand some of the fundamental questions that have impacts now, but also in the next 10 to 20 years as we try and address the 2050 global challenges to reduce CO2. So for my sins, I lead the battery degradation project in the UK, where we're interested in what's known as a full cell. So full cell, all it means is that you have a cathode and you have an anode, and they not just lithium metal, and you work out how the various components interact with each other. And so, for example, if you charge your cathode material up to too high voltages, oxygen can come off, that oxygen can go on the other side, and it can react with the graphite and cause additional mechanisms. So I'll tell you a little bit about some of that, but I want to start by telling you about in-situ metrologies, because this is what I've been developing over the last rather large amount of time. But then after that, I want to tell you a story about connecting local structure and dynamics through to mechanisms. And if I have time, I'll talk about fast charging and where we're going next. So I don't think I need to belabor the point, but it's much easier to study an operating device in situ or operando. So operando means you're actually cycling, in situ just means you don't pull it apart. And it's useful because you don't have to make lots of different batteries, and you can just study one thing at different states of charge. But the more interesting thing is that if you take the batteries apart, sometimes there are processes that don't survive disassembling. And it's not so easy when you do NMR spectroscopy just to take a battery and put it inside a spectrometer, because batteries have metal cans. And so you've got to get the RF through that you need to excite the NMR. So you've got to redesign your systems. And pretty much any operando measurement has you'd have to go some sort of thought process as to how you design the setup for the particular technique. And each will come with advantages and disadvantages. And there are other challenges. First of all, sometimes the batteries catch fire, which is a little bit of an issue. There are bigger things, like you have leads coming up. These leads pick up RF. So in this room, for example, the radio frequency, I don't know what frequency of NPR is, I think it's about 91 point something. That's the same frequency as carbon. That's sort of what causes this noise. So you've got to do all the RF filters to stop this. And then you've got the more interesting challenges associated with the diversity of different materials that have very large shift ranges, and also as you're cycling, the susceptibility changes. So over the years, we've developed new cells to look at it. This is a so-called plastic bag battery, where you use the same technology that you would to seal coffee or to seal smoked salmon. You use a food laminator and you put your battery inside and you can do NMR of this. Or we upgraded it to plastic cells that are much easier to put together. And then we design setups where we have piezoelectric motors inside our NMR cells so that we can tune the components on the fly as the materials are cycling. So I just want to give you a little flavor of the sort of things we've learned over the years. The first study that we did was on silicon. So graphite has a capacity of about 370 milliamperes per gram. If you use silicon, you can react 10 times more lithium with it. And so it's been touted for many years as the sort of ideal replacement for graphite. But what we showed in this very simple study was that if you took the fully lithiated silicon and you just let the system rest, you could watch the open circuit voltage go up, which means there's a reaction happening. And by looking at the NMR in situ, you could see the peak disappearing as this material was being oxidized by the electrolyte. And so the electrolyte's being reduced, itself it's being oxidized. And so this was the first study to show that the problem with silicon was not per se the large volume expansion of silicon as it reacts with lithium, but that it didn't form a nice passivating layer on the top of it. And that's what forms in graphite, and it's called the SEI, and that's why all graphite materials actually work. So just to give you another example, I wanted to sort of put carbon in as the theme in a lot of what I'm talking about. In sodium-ion batteries, you can't intercalate sodium into graphite. You can intercalate lithium, you can intercalate potassium, but sodium's the wrong size. And so if you want to go for a more sustainable technology, you've got to find a new anode replacement. And the thing that people use for the replacement is a material called hard carbon, which is just essentially a carbon that's heated up, that doesn't graphitize. It has enough defects in the structure that it doesn't form beautiful layers. And so what we did was to use a sodium NMR to understand the mechanism of how you intercalate or insert into these graphite hard carbon graphitic type structures. And so the model of a hard carbon is the so-called house of cards. And what we showed was that you had, first of all, insertion into diamagnetic regions, and then you filled in these so-called sodium pools with pores inside the hard carbon structures. So then just to move forward, now we used our in-situ metrology to look at a whole variety of different materials. And so if we think about what are the next generation higher energy density materials that are more sustainable, we could look at lithium sulfur, we could look at lithium air batteries. So lithium air is a reaction of lithium and oxygen to form peroxide. The problem with a reaction like this, it goes via superoxides. Superoxides are basically the radicals that inside eat up, cause cancer and will react with everything. They do the same thing in a battery. They will eat up the electrolyte and cause degradation. And so we've developed over the years oxygen methods to track what's going on. And similarly, we use sulfur NMR to track what goes on in sulfur batteries. So just to sort of give you one more example, again with carbon. So the other, if you want to do a high rate electrochemical cell, you might use a supercapacitor. So supercapacitors bridge dielectric capacitors of batteries in that they have higher energy density, not as high as batteries, but they also can charge in principle faster than battery systems. They're used in they're in your mobile phones as flashes. They're also in the emergency exits of the Airbus systems. And they work because they have these beautiful hierarchical structures. And so you take a coconut, you activate it, essentially the same coconut systems that you would have in an activated carbon that you would use for water filtration, and you form these hierarchical structures. These strands here are the PTFE strands to hold the thing together, and then you can store charge by simply inserting ions and at the double layers of these carbons. And what we did with our in-situ NMR, this is now a while ago, was to look and ask the question, how do ions insert inside carbons? And so what you're watching in real time is the fluorine NMR of the anion in this salt, tetraethyl BF4- in acetonitrile. So this is the signal as you're charging up and down of the ions going in and out of the pores. And the signal is shifting backwards and forwards as you're inserting. In this case, we're going positively, so we're inserting holes into the system. We're charging up the carbon sheets, and we're reducing the aromaticity of the carbon. And what is happening there is you're getting a reduction of the aromaticity, you have a reduction of the local field on top of it, the reduction of the so-called nuclear independent chemical shift that you're seeing there. So you're actually able to track the extent of hole doping in these carbons and say something about the mechanisms of intercalation. But that was nice from a sort of theoretical perspective, but this method actually allowed us to ask a very simple question that hadn't been shown experimentally before. So if we imagine an activated carbon, so again, these are the activated carbons that you would have in a water filtration system. We all know that the ions will go in, so at 0 volts we've got equal numbers of negative ions and positive ions. And surprisingly, it wasn't known before whether you would store charge. So let's imagine we do an experiment where we charge something positively. You could either kick out the positive charge for charge compensation, or you could bring in the negative ones, or you could swap them. So you could do an ion expulsion, an ion exchange, or so on. And so what we did was to look at this and quantify the ions on charging to positive versus to negative. And we showed that if you charged negatively, you actually sorbed cations, whereas if you charged positively, you had an ion exchange mechanism. And then by doing pulse field gradient spectroscopy, we were able to show that if you stuff lots of cations in your material, not surprisingly, the diffusivity of the ions inside these pores went down. And so the sort of moral of the story was, if you want to get high rate, you want to avoid these types of carbon sorption processes. You want to have an ion exchange process so that you can still move the ions. And so more recently, we've looked at how to optimize these carbons for these processes. There was a very nice work of Patrice Simon a few years ago that said you wanted pores about the same size of the ions, the solvated ions, and that this was a descriptor for capacitance. Our more recent work with my collaborator Alex Force showed that actually you could have carbons with very similar pores and you'd have very different capacitances. And actually the better descriptor that we picked out from these NMR signals was the degree of coherence of the carbon sheets. And as the system got more disordered, non-intuitively the capacitance went up. And that's because if you have lots of defects in the carbon sheets, you start pinning charge near these defects, and then you can pin the ions nearby. This was a paper just published very recently. And then Kara Fong, who is a postdoc in my lab with Angelos Michaelidis, has been doing some very beautiful MD simulations using machine-learned force fields to really understand the nature of ion pairing in these types of related systems. Okay, so that's my introduction on in-situ metrologies. I want to now lead you through a story where we're going to connect local structure all the way through to mechanisms for how materials intercalate. And so the story starts with this material NMC811. So this is the cathode material that's in most of today's electric vehicles. It's a layered compound like lithium cobalt oxide, but you've replaced 80% of the cobalt by nickel and 10% by manganese, so that's the 811. And we do NMR of this material. And I've studied these materials, or me collectively and my group have studied them for many years, so we know how to interpret these quite complicated spectra. So we're going to do ex situ NMR. We're going to take different batteries at different states of charge and try and unpick what these sort of broad blobs mean. And the sort of main thing is that when you take this material, it's a mixed nickel 2 to nickel 3 oxide that gets oxidized to nickel 4+. So for those of you who've forgotten your inorganic chemistry, nickel 4+ is low spin D6, it's diamagnetic, and the only paramagnetic ions that are in the system are manganese 4+. And when you pull most of the lithium out, the lithium remains near these paramagnetic manganese 4+ ions, and that's why you get these spectra. And so the sort of take-home message is we can actually interpret these spectra. The thing that we can't interpret is in the middle, where things get quite sharp. And when NMR signals, so this is at lithium NMR, so I'm looking at the local environment around the lithium, and when I pull out 10% of the structure, I see this very broad feature. I heat it up and not much happens. But if I pull out 25% of the lithiums, I now have vacancies in the lithium layers, and the ions can start to move. And the signature of motion is quite clear from when you heat this material up. Because the ions are moving, they're changing their local environment, and so you get what's known as motional averaging. So the NMR only sees the average environment of the ions moving in these layers. And you can see by the time you got rid of 50%, you've got very high lithium mobility. And this, to a material science audience, is not that surprising. You have vacancies, and so you have room for the ions to move, and you actually needn't die vacancies for it really to go fast. And so what Katerina, my postdoc, did was to simulate these spectra and extract the hopping rates for transport. And so if you go from about 20% removal to about 70% removal, you have hopping rates of about 80 to 100 kilohertz. So these ions are moving very fast in these structures. And we can get an activation barrier for that transport by just varying the temperature. So there's 2 points. Why do you get increased mobility? One is that the layers increase, and then at the end they collapse. And so that collapse is why you actually stop moving the lithiums at the end of charge. There's another phenomena which I worked on with a former collaborator who may be familiar to some of you in the audience. And that's associated with, as Gerd Seder, that's associated with the charge of the ions on the layers and above. And if you oxidize your nickel from 2+ to 4+, you have, if I'm a lithium ion, I'm hopping from octahedral site to tetrahedral site to octahedral site. There's a very short contact there, and that short contact gives you the activation barrier, and the higher the oxidation, the bigger the Coulombic repulsion. So this all makes sense. So I'm going to move now, in the spirit of Millie, from the cathode to the anode, and I'm going to think about graphite. So again, we all know graphite. We take graphite, we have these various stages. So stage 4, for example, this L means less dense, it's or light or low. It means, and the stage 4 means it's every 4 lithium is filled. And you go through stage 4 to 3 to 2, and then you form the dense stages 2 and 1. And the thing about the dilute versus the denser stages, and this was something that Millie worked on, is you have very different conductivity. And so you go from the dilute stages that have very low conductivity to the dense ones that are very conducting. And you can see that by NMR. So this is the dilute stages, which have a very small shift. Once you form the dense ones, you have this large night shift, which is a measure of the density of states at the Fermi level as measured by the lithium. And then the other thing that's interesting about it, that again comes out from the NMR, is you can, via a technique called a T1 row measurement, is you can quantify the diffusivity. And it's very easy to get the diffusion coefficient at the so-called T1 minimum. And so the minimum is where the transport is the same frequency as the Larmor frequency. And so as you go from a dilute stage to stage 1, you can see that the diffusivity here is the same, but the temperature at which you achieve that diffusion coefficient varies. And so the diffusion coefficients in the dilute stages are much faster than in the dense stages. But they're of the order of 10 to the minus 11 centimeters squared per second. So the question I wanted to then ask was, how does this mobility affect the intercalation mechanism? And to look at this, I've been working with my colleague Akshay Rao in the Cavendish. And so if you want to understand how particles are inserted, you typically go and find your local synchrotron. You set up very clever, nice experiments where you focus the synchrotron beam at your particle and you watch what's going on. And it's great. You can get beautiful information, beautiful spatial and temporal resolution, but you get the reality is you often get beam damage, and it's not easy to get a lot of beam time. So what we did was to do something much more simple. We were inspired by the work of Phil Kukuru at Oxford, who developed a lot of very good microscopy techniques called ISCAT, it's a rather horrible name, to look at fluorescent biological systems. So biologists they tag things and things move around and they can watch things very rapidly. Here we're just going to use this method to look at scattering of a particle. Now scattering is proportional to polarizability, and the degree of scattering will be dictated by the differences in the polarizability of the two medium. So if you've got a particle, it will be the difference between this particle and the medium around it. It'll be lower resolution. We've got resolution of the order of 300 nanometers. It's a little bit better now, but we don't have any direct chemical specificity. So actually, and I hypothesized that we should maybe be able to use this to follow how ions went into material. So that's the way we went into it. This was a story of 2020 or end of 2019, and I said, let's keep it really simple. Let's use a particle that's big and we know what's happened. So we took our friend lithium cobalt oxide. The student Alice Merriweather made some beautiful experiments where she diluted the lithium cobalt oxide in a carbon matrix. We just took a Raman microscope cell, and so you can see the basal plane, the top of the lithium cobalt oxide, and the electrochemistry is doing its normal thing. So lithium cobalt oxide has a metal insulator transition, which is this peak here that is shown in the DQDV plot, and this process is an ordering transition at lithium 0.5 that I'll explain in a few seconds. So this was the first imaging of ISCAT. So what you're seeing is the SEM, and these are the pictures. And we're focusing on the flat parts of these particles, but we're going down about 300 nanometers. So this is not a surface method. We are really looking at bulk phenomena. And then we got this image in March 2020, and we had all of the pandemic to work out what was going on. So this was the one positive for the pandemic for me, was that we could actually think about it. So what you're watching is, this is now lithiation. That's the Li 0.5 phase transition. This is a solid solution. And this is the two-phase reaction. You're going to see a nucleation across there. But now watch it in the other direction. So we're going to start fully lithiated particle, and you're going to see that actually things start to emerge from the edges and you come shrinking in. And then you have a solid solution. And then this thing coming up here is the ordering transition at Li 0.5, ripping through this particle. So what's going on? So there was this beautiful paper by Martin Bazant and Yang Xiaohorn, who had examined different mechanisms and thought about why you would get different types of intercalation processes. And they separated these two mechanisms, the so-called shrinking core mechanism and an intercalation wave mechanism. And if you look at our particles, this is exactly what's happening. Here you've got a nice shrinking core. This is shown sort of in snapshots. But on the way back, you're lithiating and you're nucleating one thing and it's moving across. So why do you have two different mechanisms on charge and discharge? So what my former postdoc Quentin did was to try and model this with continuum modeling. And we just think about why this might happen. So we start off again, we've got this lithium-rich phase. The lithium is stuffed. The lithium isn't going to go anywhere. The diffusion coefficients are very, very low. And then we have a metal insulator transition with an immiscibility gap to form this lithium poor phase that's metallic, but it's also got much higher ionic transport. And so if you think about your particle, I'm here in my pink phase, lithium isn't moving. I pull the lithiums out from the edges, and it's so much easier to keep on pulling lithium out of the blue phases, and so the particle that gradually has this shrinking core. But I now go in the opposite direction. I nucleate somewhere, and now I've formed a pink phase. That lithium isn't going to go through the pink phase. The only way that pink phase can grow is if it goes into the blue phase and adds to it. And so by very definition, it's really going to have to grow out in that direction. And in sort of, in reality, it's the trade-off or the rate at which you can pull ions in and pull them out, the J, versus the relative diffusion coefficients of the two phases that explain this. And so just for completeness, this is this ordering transition I was telling you about. This is you form a phase, Li 0.5, where you have ordered vacancies, lithium, vacancies, lithiums. So you've lost the threefold symmetry of lithium cobalt oxide, and you can sometimes form three domains in a particle, and sometimes it goes with just a single domain. So that's lithium cobalt oxide. So I just want to move on from lithium cobalt oxide because, of course, this is the material of the 1990s, just to talk about NMC materials. And the question I want to talk about was, again, this discovery, at least from our hands, that if you started to pull lithium out of these materials, even though these materials in principle were a solid solution, they also had these two-phase reactions. And we said that this was associated with the particle level phenomena. Meanwhile, there's a very nice paper by Will Chu's group and Martin Besant, who commented on the fact that there was probably an electrode level process that caused this. And so we wanted to look at this phenomena by our ISCAT method to see if we could at least look at it at the particle level. And you can see now we've out of the pandemic, we've improved our microscope, we've got rid of some of the artifacts, and you can see that there's a lot of heterogeneity going on. And if we just look at one particle here, this is a differential image, you can see there really is a shrinking core at the particle level. And so the question then is this a thermodynamic process or is it a kinetic one? So lithium cobalt oxide has a two-phase reaction. As a metal insulator, that's a thermodynamic process. But this one is a kinetic process caused by the differences in diffusivity, and I'll show you that in a second. But the way to check that is just to stop, let the system relax, and if it relaxes, that indicates it's kinetic. And so what's going on is very similar, though, to the lithium cobalt oxide system. You start off your material, it's stuffed, the lithium's not moving anywhere. You start pulling lithium out from the edges, and again, it's easier to pull it out from the red phase, and so it collapses in a shrinking core mechanism. And what's nice is, because now we have the lithium diffusivity from the NMR, that's why I went through the exercise and showed you the NMR. So we had the hopping rates, we have the hopping frequency rather, we know how fast the distance over which hop is, so we can then use that to calculate the diffusivity from the NMR. We know the voltage of the curve tells us the energy or the delta G associated with pulling the lithium out of the structure. And so we can put that into a nice continuum modeling. We're now collaborating with Norman Fleck and Vikram Deshpande, and Shri was the postdoc on the project, who built a much better continuum model of it with a particle that looked like our particle, and he was nicely able to replicate the shrinking core model of the system. So that was the NMC. I'm now going to go back to the anode and talk about graphite. So this is a particle of graphite doing its thing. So this is a stage 2 to stage 1, and it's really beautiful. You can see this particle and watch these intercalation wave mechanisms going through it, and then you can watch the end process. Now I want to just walk you through this one more time. So this is the intensity. There's not a lot going on. And then suddenly, but you can see the stuff going on. I'm going to unpick that in a minute. And then it suddenly changes when you go from a stage 2 to stage 2L to 2. So let's just look at what that graphite is. This is the ISCAT image. This is the SEM. And you look at that particle and you think it's actually a pretty single grain material. But yet when you unpick it like this, there are multiple domains within it. So what can we actually do with this ISCAT for graphite? So Millie, in her solid state physics course for the MIT undergraduates, nicely explained what's going on here. So you've got a dramatic change in the conductivity as you go from the dilute stage to the dense stages. So the conductivity goes up, and so the polarizability changes, and you get this very large change in the scattering, and that's exactly what you're seeing here. So what can you do in terms of using this information? So this movie is a new one that never works. So you can explore nucleation. So this is at low temperature, and if you watch, you can see that there's sort of multiple nucleation events. If you go up in temperature, if I get the movie to work, there are fewer nucleation, but actually at the highest temperature, you can see it's actually just a single nucleation event. And so the differences in the transport of the lithium ions as a function of temperature have a significant impact in how these materials operate. And so this is now showing you the differential images. So this is the stage I was talking about. So this is stage 2 to 1. And if you just take snapshots, you can see these intercalation waves moving across. And so this all makes sense. This is nice. This has been described well by particularly some papers by Martin Besant. But the one that's completely different is what's going on here. And if you look at the individual domains, you can actually see that there's domains being lithiated semi-randomly and continuously. So if you're epileptic, please look away in the next image, because this is what's known as a differential image, and it's flashing. And so this is the domain in the first stages, and you're seeing these events of different layers looking as if they're almost uncorrelated as the different layers are being filled. And you can track the correlations between them, and there's definitely relationships with one following another. But if you look at the intensities, it's not a smooth, solid solution as the electrochemical profile would suggest. It's these little series of steps. And what those little series of steps correspond to is the individual filling of one layer at a time, which we can actually see step by step in these simulations. And so in retrospect, like all experiments, this is obvious, but actually previously people just thought about this as sort of a solid solution process. And it sort of starts to resolve the questions people have in terms of how do you go from alternating 3 layers to 2 layers and to 4 layers, or vice versa. And we can model this with, I won't go into great detail, but we can model it with a very simple Ising model with different degrees of relationships between the layers and also defects within the layers. And this is for reminiscent of something called avalanche behavior, which you all know what an avalanche is. Something goes and it suddenly goes, and it's associated with the sort of pinning in the layers. And then once you've overcome that activation barrier, then the whole thing goes, and you get these types of characteristic phase transitions. So it's interesting, it's a totally different mechanism for graphite that, despite this material having been worked on for many, many years, hasn't been seen before. So let's just think about why we can't charge faster. So I've talked about the NMC materials and the LCO materials, and as long as you're working in the right regime, between about 20% and 70%, actually the lithium mobility is pretty good. So why can't we just charge our batteries infinitely fast? Well, this is a Samsung cell that we put 10 amps through for 1 minute, and this is not a recommended experiment. Heat thing, and it goes to above 60 degrees very quickly. And the 60 degrees is the temperature at which the SEI, the passivation layer, starts to fall a bit, to fall apart. The cathode, when it's oxidized, is metastable, and things go horribly wrong. The other thing is something we like from an experimental point of view is that if you charge too fast, instead of intercalating nicely into graphite, you form these dendrites. These dendrites look very beautiful, but they also have caused incidents like the Dreamliner plane was at least thought to be associated with a dendrite incident. So we do a nice NMR, we can track our dendrites by NMR, and so the thing about NMR is that it only has a certain depth. It can go through a metal called the skin depth, and that allows us to track the dendrites being formed. So this is the dendrites forming. This is the passivating SEI forming on top that we can track. So we can do beautiful experiments. We can do magnetic resonance imaging experiments, and we can track them as they're forming, and we can relate that to the SEI formation. So that's all nice from a sort of from an experimental perspective, but it doesn't really help us in terms of the fast charging. This is now more recent experiments where we're looking at the full cells. We've got our NMC material, we've got the graphite, and we're looking at charging, and we're charging at increasingly low temperatures, and you can see at low temperatures you're forming lithium plating. And this lithium plating issue is why in regenerative braking you can't utilize all of the kinetic energy to charge your battery because of this worry about lithium plating. So how do we design for fast charging? Well, we have to find a material that operates at a high enough voltage to avoid the lithium plating, and it has to have high lithium mobility. And the sort of prototype material that many of us as material scientists would think about would be a perovskite structure or rhenium trioxide structure. It's got lots of holes. Why can't we use it? And the problem with it is that lithium is too small for most MO3 structures, and so the units rotate and they clamp the lithium's in place. So lithium rhenium oxide is a terrible, even despite its price, is a terrible battery material. So what you can do is to think about how you pillar the structures to prevent those rotations. And so you can take a material and you can conceptually do a shearing operation. So we fuse the octahedra together, and when you do that, you put a lithium inside, you can no longer rotate. So you can just formally imagine that, and it's stuck. And you can do it in 2 dimensions, and that's when you get this HNV205 phase, and you form these blocks, And again, the lithium is really there, it's rigid, and you get, in principle, get very rapid lithium mobility. And so that's what my former student Ken Griffiths did. He went through a whole series of different compounds, and the best in class he discovered in his PhD was this niobium-16 W5O55, which for obvious reasons is abbreviated to NWO. And so this has a block structure of 4 by 5, and it has a very high rate. And so with very little optimization, he was able to get a 20C rate. So 20C rate is a 3-minute charge. And the thing that's limiting that is not the material itself, it's the lithium metal that he's charging it against. And again, with very little optimization, he was able to get materials that were lasting for a very long time. And so then we can ask the question, well, why does it work? So one way of doing that is to do pulse field gradient spectroscopy. So you put a gradient across your material, you wait for the system to move, and then you quantify the echo, and you end up getting diffusion coefficients of about 10 to the minus 11 to 10 to the minus 13 meters squared per second. So let's just reflect for a few minutes on what that means. So let's compare our materials with the common other conductors. So if you're a liquid electrolyte, your diffusivity is about 10 to the minus 10. So if you're trying to do a 3-minute charge, it means you can move about 330 microns in that 3 minutes. So you can move from one side to the other side of a battery. So battery electrodes are about 150 microns or 100 microns, depending on whether you're optimizing for power energy density. But if you're a graphite, and this is the 10 to the minus 15 that I showed you earlier on in the talk, that means that in 3 minutes you can only move a micron. And so you've got issues again of the plating that I was talking about. And so you need to sort of nano size to get the rates. But if you're an NWO, you can move 33 microns, which means you can make these chunky monster particles that we made, and you don't have to nano size, reducing cost and reducing degradation. So that was fun. Not only do they move fast, you also get very good electronic conduction because you've got these edge-sharing octahedra that go down the material in the direction of the tunnel. And if you do DFT calculations, you end up with these, the first electron goes into these block orbitals where you have at low temperatures antiferromagnetic coupled electrons in one block and the other one, but the second one forms a band and it becomes metallic. And so then this is now the same picture of the NWO, the same now battery of ARM battery, and in 100 seconds you can see it only goes to 40 degrees, and then it's put into a Dyson vacuum cleaner. Before Dyson went off to Singapore. I wouldn't do this anymore. But anyway, second story. And now this is it in a startup company, Niobolt, and this is a little robot charger that can go to your car or can go to somewhere you need charging, and then this is a cheaper variant that's now in a car. So there's just an illustration of going from the fundamental through to applications. I want to end with one quick story. Do I have 5 minutes? Yeah. With, again, to return to the sort of theory of the theme of graphite and Millie Dresselhaus, but this is an even older story. So I've been trying to, like many people in this audience, really understand what is the nature of the passivating layer that grows on both graphite and lithium metal. And I thought, well, I could go back to this very early experiment of Albert Overhauser. So chemists may have come across something called a NOSI, or a nuclear Overhauser effect. And we all imagined that this was invented for organic chemistry and biology. But actually, Albert Overhauser, many years ago, said you could actually zap the electron spin irradiation. And if you looked at the energy levels of your a coupled system in lithium, so you looked at the lithium spin, so the lithium is the this spin here, and you looked at the electron ones. If you irradiated the electron spin resonance and you had the right relaxation mechanisms, namely this relaxation mechanism was faster than the other ones, you could actually enhance the magnetization of lithium metal. So this was in '53. He was in Illinois, and his colleague down the road, or in the next apartment, replicated this experiment the same year. So this is an experiment by Tom Carver and Charlie Slichter, and what he did was he had little bits of lithium metal in a dilute matrix, and he got this massive enhancement of 110. And the signal, so he's down at 3 millitesla, so very low frequencies, and he didn't even get the signal lithium metal without irradiating. He worked it out based on comparing with some proton experiments. So this was sort of experiments of 1953, and I thought, well, maybe we could do this in 2023, or 2020 more accurately. And so, but since then, we've upped our fields, and people like Bob Griffin in the chemistry department have worked a lot on this method called dynamic nuclear polarization, or DNP. And the challenge has been to try and find gyrotrons or mechanisms for irradiating the electrons at these much higher fields because of the difficulties of using microwave technology. And so here we are in 2020, and we've got an enhancement of 8. And it's not because we're particularly pathetic, it's because we just don't have the same high power as in low fields. But it's exciting, we can partially saturate it. But the most interesting thing was we could also polarize the signal of the SEI, so the covering of that lithium metal. And so then the question is, what can we do with this? And so the first question we had was one associated with what is, so people, Bette Gallant's group is a particular pioneer in this area, has spent a lot of time trying to work out what's in this SEI. And they quantify different parts, and you can do XPS, and you can sort of go down to deeper levels. But what's really difficult is to really look at that interface between the lithium metal and the SEI. But we can do this directly. And so in this experiment, we transferred the polarization, we enhanced the lithium signal, and then we transferred it to the fluorine. And surprisingly, there was no lithium fluoride. And the lithium fluoride has been thought to be the sort of major critical component of the SEI, but there isn't any. But if you add an additive like FeC, which is this fluorinated carbonate, then lo and behold, you have some lithium fluoride. So then just to sort of end, well, what about graphite? So graphite, because it's conducting, here's the ESR signal. Without going into all the details, it's conducting, it has this Dysonian line shape. It's all very well discussed in this beautiful review article of Millie in 1981. You can separate the different line shapes depending on the conductivity for the different stages. And, my student put in this massive image of this is a graphite, and this little arrow is meant to show you that in there are some dendrites. So they're very difficult to see, but you can see them beautifully by the ESR. So here's the signal of the lithium LiC6, and here's the dendrite signal. And what that means is you can irradiate selectively either the LiC6 or the lithium dendrite, and you can enhance this passivating layer on either the carbon or the lithium metal. And so this is an example where we're irradiating the lithium metal. And you're seeing we're getting these massive enhancements of that lithium metal and smaller ones of the lithium carbon itself. And so what that then allows us to do is to ask the question, how does the SEI differ on LiC6 versus lithium metal? And the sorts of information we can get out is that this is on the lithium metal, that the signal closest to the lithium metal is a lithium oxide. There's probably also some acetylene systems there. They all resonate in this neck of the woods. It's very similar to what Bette's group has seen. And if you look at the lithium LiC6, there's lithium hydroxides that are present in the lithium metal, but not in the LiC6. And so we're now in the process of using this method to really unpick what a lot of the speciation is. And so with that, I think I'm sort of more or less on time. I'd like to end by just, here's the full cell lithium cobalt oxide that I started off with, the Sony rocking chair battery with the lithium cobalt oxide on one side and the graphite on the other side. So that's for the sort of entertainment while I finish off the conclusions. So I hope I've illustrated that we've developed all of these different in situ or operando metrologies, from NMR to MRI to these now optical methods, which have allowed us to really unpick fundamental processes at the atomistic all the way through to the particle level. And then in the fast charging example, I hope I illustrated that we could then pull through some of this understanding to try and make some technology. And then more recently, we've been trying to develop these methods to actually look at interfaces and trying to design approaches where we can enhance specific parts of the signal. And so in this DNP example, that's one where we can irradiate specifically the electrons in one component over the other and really use that to try and understand the metal diamagnetic interface. And Obviously, we can look at interfacial processes by electron microscopy, but it's very difficult often to get the chemical specificity. And so hopefully some of these NMR experiments allow you to do that. And of course, this wouldn't be possible without my great research group. This is us on a hiking trip a couple of years ago. I've mentioned a few people on the way, but I want to really highlight Ollie and Barish, who started the In-situ NMR. The NMC work was Chao Chu and Katerina Merker and Phil Reeves. The niobates was really pioneered by Kent Griffiths, who's now on the faculty at UC San Diego, with Lauren Mabella, who did a lot of the PFG. She's at Columbia. The DFT, I had a lot of collaborations with Andrew Morris, Rangeet and Anna and Svetlana, the dendrites. The ISCAT was really a lovely collaboration involving Akshay Rao and Alice, the former PhD student, with Chris Schneiderman, a postdoc, and Norman and Shri and Dave Hall and Norman Fleck did the modeling with me, DNP, Didi Wrinkle and Mike Hope, and Supercaps, the whole large team, but largely Alex Force and my collaborator Dan Frankel. And thank you very much for listening to me.
Claire, thank you so much. That was extraordinary talk. What is going to follow is Professor Yatming Cheng is going to have a brief chat with you. So please join him on the stage.
Okay, thank you. On the stage.
Now, I understand that the audience has the ability to post questions. There we go. All right, wonderful. And so while you're thinking about your questions and posting them, they'll show up here. You know, the thing about fireside chats is you have to sit down.
I know, sorry. I felt a bit odd, but you're not sitting.
Secondly, where's the fire?
There's no battery fires, so.
No battery fires, that's right. That would have been a beautiful backdrop for our discussion here. Now, so let me kick things off and ask Claire about the view towards climate change in the UK today. Right? So as you know, and we discussed earlier, at MIT we have the Climate Project, a pan-MIT effort. Sally Kornbluth has doubled down on climate since the last administration, Raphael Reif's. And so this is going to happen at MIT, and we had an election a week or so ago. That's not going to affect what we do here at MIT to any significant extent, I believe. Right? Now, what I want to ask you is, you know, what's the view in the UK? You know, at the student level, at the university level, what's the climate on climate change? Right?
I mean, I think that the UK is, I think the distinction in the UK, it's pretty clear cut that it's in law climate. We have to phase out electric vehicles by the end of the decade, and that's now legislation. Now, whether it happens is another matter, but that frames the conversation very differently than particularly in the US and now. And I mean, maybe that was different 2 weeks ago. But you have a very active student body, and you have these sectors in the UK society. I mean, we have Extinction Rebellion. We have these are the people who have been variants of Extinction Rebellion who've been gluing themselves to parts of the equivalent of I-95 and the train stations. And so it's a very active body. I mean, we are, as a university, we're not allowed to accept money now from fossil fuel companies.
Yes, so that you mentioned that earlier, and that's a pretty dramatic move. And
that's coming from the students. That is not something that the academics are. There's some very disparate opinions on it, but it's the students who pushed it, and it's part of the protests. So our students are quite strong in the lobbying groups. Yeah. Now, in terms of the university, we have Cambridge Zero, which is our sort of umbrella organization for action. But it's very much policy, and the environment is headed by a woman from the British Antarctic Survey, and that's very much shaped what she's interested in doing. And so we've been weaker on the tech, although that's something that we're trying to do at the moment, because we have a very strong track record in a lot of energy systems. But I think, MIT does these things well, partly because it always has more money, or at least that's the perception from the outside, but you may disagree with that.
Well, you did say that, I asked you earlier today when we met, so what do you see as the difference? And you said, in the UK, we do much of the same thing, just with less money.
Exactly.
Right.
Yeah.
And so, and also you have a...
And I'm not saying that's a virtue, it's a reality. I would be very happy if it was
That's right, maybe you're more efficient.
Yes.
There is also the rest of Europe. Right?
Yeah.
So, what is the dynamic between the UK and the rest of Europe on climate these days?
Well, I mean, you have the election last week as the elephant in the room. And of course, we have Brexit as the elephant that sort of floats around somewhere in the channel. So because we've, in the last few years, been part of this negotiation to be part of Horizon 2020, which is the funding mechanism from Europe, and the EU linked that with immigration. So it was almost used, funding was used as this sort of thing to beat the UK over. But anyway, we're back. We're in Horizon 20, and we're very much trying to give the impression of being outward facing and wanting to collaborate. And so that's been a major focus to re-establish the networks that were broken as part of the whole Brexit period. Because there was this time where most of the time we could be a part of it, but we couldn't lead any collaboration. So that's from a sort of, from an academic perspective. I think the whole other perspective is the industrial one. So because of Brexit, we don't have an ability to trade freely, but yet the reality is that a company that makes something in the UK, the EU is their major trading bloc. And so you have to, in the same way that the US, if you're making something in one state, you still have to obey California's emission requirements. So there's an incentive to obey the requirements of the whole of the US. In the UK, there's an incentive to obey the regulations of the EU. And the thing we talked about earlier on is the need to, manufacture as much as possible within Europe.
Right.
And so that's influencing a lot of policy, influencing the need to have materials that come from within Europe. And of course, people who've been to Europe, we're not a country full of mines, and there's not a lot of natural resources.
So there are a number of parallels here that you've pointed out. Now, so back to the industrial aspect. So I may be a bit of an outlier, but I think that our election is probably not going to change the progress of climate mitigation technologies as much as some think, for a couple of reasons. One is 2016 to 2020, there was actually a very fertile period for both the development of new technology and creation of new companies here in the US. And here we are in 2024, and a number of those companies now have grown to the point where the economic benefits are seen. And those economic benefits, for instance, in manufacturing, are predominantly in red states. And so where job creation is taking place, what we're seeing now is that politics are put aside, and better jobs, for example, more jobs, better jobs, are carrying the discussion. In the UK and I would say in Europe more broadly, do you see those economic benefits from the energy transition yet?
Yeah, I think it's a really good point. But I think the distinction is that the US has been better. The UK has been dragged down by Brexit, and that has made a difference to the economy. And Europe hasn't bounced back with the same speed after the pandemic as the US. And so that's dampened a lot of this. And I think, what it's made an issue that I think is very relevant to the US as well, is trying to think about how the transition to a more sustainable economy is for everyone. And it's not just those who can afford their Teslas or the equivalent. And I think that, and in the UK, you have to talk about the red states and the blue states. We talk about the north-south divide. And it was the levelling up agenda, which was a term that was introduced by Boris Johnson, who we can discuss that. But with that leveling up, they even created an agency for leveling up. Now that's been got rid of, but it doesn't. It nonetheless, the Labour is under even more a political challenge, because the Labour Party, which was out of office for so many years, didn't get in because the traditional Labour areas in the north of England all voted for the Conservatives. And so that's hampering them even more. So it's this balance between how do you do what's actually in law, which is to, as I said, to think about removing removing petrol cars, gasoline cars, and rolling in electric vehicles, and then trucks are next, yet doing this in an economy that is not as vibrant as this country. And so I think that's what's making the Labour government, putting it in a very difficult spot. And they've wanted to be more transparent, but it's not easy. So I don't know if I answered your question. I think it would be great if there were more companies in the UK in the same way that start to see this as a way of, to be blunt, making money. I mean, yeah.
And you had mentioned to me earlier that the ARPA-E model, for example, is being exported to the UK currently.
Yeah, even with ARPA-E people. But again, as I said to you earlier on, with smaller numbers. But what's interesting, unlike, and maybe I'm wrong because I've now been outside the US for long, that there is also more of a model to have ARPA-E type projects that involve Africa and other parts of the world to think about democratization of energy. And so, that may be that the funding model is different. The UK traditionally has put more money in aid, and some of that aid funding has been associated with science. And so some of that's been folded into the to our ARPA-E, which I think is also interesting.
Great. Thank you for that. And so feel free to submit questions, and we can go back to some. You can ask some more technical questions if you like as well. Vladimir, do we have to stop?
No, we have a couple more minutes. Just raise your hand if you have a question.
Okay.
Because the pigeonhole is not behaving the way we expected.
Okay. And while we wait for that, I want to ask you a little more, a somewhat more personal question here. So, you and I met in almost 30 years ago. And I believe that, at the time you had left DuPont and were an assistant professor at Stony Brook. And, we're now both considerably older. And now you're Dame Professor Clare Grey, right? And, I wanted to ask you, what's that like? I mean, when students come into your office now, how do they address you? Do they have to bow? Do they have to
I was going to say they bow.
Tell us about that.
Oh, they bow, yeah, totally. I mean, what is there to say about it? I mean, it's a slightly embarrassing title. And I went through,
and now,
I did look,
knighted.
There's a website of people who
You were knighted, right? So knighted is still the right phrase
it's
for,
sort of,
for dame.
Yeah, it is actually. It is, yes. It's just that the men are called their knights and they get swords. They get given a sword, but the women get nothing.
So you didn't get the sword?
No sword, yeah. Anyway, there's a website of people who said no, but in the end I decided, there are not many women scientists who get this honor, so I should just embrace it, but it's okay.
It's a wonderful honor, and you should embrace it. I think it's wonderful. So congratulations on that. All right, do we have some questions? Hands? Anyone? Yeah? Oh, Lynn, Professor Lynn Hobbs, please.
I just have a very small Millie Dresselhaus. Yeah, I have a small Millie Dresselhaus related comment. She and I and some others were working on transmission electron microscopy of the lithium intercalation of graphite back in 1981, which is when some of your comments were addressed initially. And those studies were bedeviled by the unavoidable but indeterminate electron beam heating in the electron microscope. And so I was extraordinarily excited in the imaging methods you've dreamed up, which enable you to look at the temperature dependence, which is clearly hugely hugely important in these classes of materials and in this kind of technique.
Thank you.
Thank you.
Yeah.
Please.
Hi, my name is Jacob Siegel. After your work with graphene doping with nitrogen, do you see that if graphene purity increases and manufacturing techniques are improved, that it would be a viable material for the cathode?
So you saying, so do I think nitrogen-doped graphenes would be good for a cathode?
Yeah.
Yeah, I mean, most graphites, even with nitrogen, they'll be down on the anode side. So I think it'll be an anode. You know, the problem you always have is that graphite is so good. Mm-hmm. And if you put nitrogen in there, it could, in the application I told you of supercaps, where you're just storing things on a double layer and you've got solvated ions, if you start putting in defects, anything that pulls the ions closer together gives you higher capacitance. So I'd probably look for it in that sort of application. I mean, there is some, you know, people do talk about nitrogen-doped, boron-doped graphenes and graphites, but the problem with batteries is you just want stuff, and anything that's fluffy, you know, is bad. And anything that's more fluffy, of higher surface areas, more degradation. So I say do a supercap.
Okay.
You know, maybe I could
you can.
Just take that question and add a question on top of your question. It's very good. Graphite is great, but it's a little too close to the lithium metal potential for comfort.
Exactly, yeah.
Right? Why is it in lithium-ion batteries that we have, you know, lithium metal, we have graphite, but then the next best thing is lithium titanium oxide,
all
which
these
is
NWOs, all 1 volt higher.
a volt and a half higher there.
Yeah.
And so why is this demilitarized zone between two? What we really need is something that's about 3/4 of a volt off of lithium.
There's vanidates, and so they're 0.9, titanate's 0.9. I think one of the challenges, if you look at the lithium vanidates and the lithium titanates, is you're having to make them lithiated to get there, and they're a pain to process. You can't do it in air. So air is about 2.9 volts or 3 volts, and so when you're making things, you're always making things in that oxide. And if you're making it unlithiated, so that's half of it. And yeah, I mean, that's the periodic table.
Well, we clearly need another one.
I mean, you can, you know, as you're suggesting, you can dope graphites, but again, you're creating distributions of stuff, and but I do think it's the metal oxidation states that you want that get you in that 0.6, 0.7. You're making them lithiated, and then it's a question of how do you scale it as well.
All right, I think we are out of time, unfortunately. And so please join me in thank Clare again for a wonderful lecture and discussion.
Thank you.
Thank you. That's great.
There are many materials in the world. At MIT, we have an absolute pleasure of working with many of them, including glass. So our students, together with our amazing staff, run the glass laboratory, where glass is extruded in many beautiful shapes, including, given the fact that we are at the Thanksgiving season and a pumpkin is a symbol of it. We have made a glass pumpkin as a memento of this particular day. It has a little MIT logo on it as well, embedded in the glass. Thank you so much.
I don't know what one does.
I would like to give this to you as our very small token of appreciation. Thank you so much.